Hello everyone, this is Andrea from Hero Academy and Brain Boosters. Today I came with another chapter. We are in chapter 16. This is segmentation. As you know, we are using the book Operating Systems 3 Easy Pieces. So let's get into it. In chapter 15, we discuss about address translations and how virtual machine and physical memory and address space, how we translate the virtual address into physical address with bound and base and bound system. So I invite you to check the video. So in this chapter we are going to see the problem of segmentation. So the main idea, what is it? Inefficiency of the base and bound approach. As I have told you now, the base and bound approach is whatever address, the virtual address space we have a formula to get the physical memory, the exact address. We have to add the base address of the base address which is assigned with the operating system into the virtual memory address. Then in that way we can find the reference efficiently. So as you can see here, we have the address space, the virtual memory 16 kilobyte. So in this address space you can see we have the program code, we have the heap, and we have the stack. And as you can see, from 0 kilobyte to 2 kilobyte we have a program code, and from 2 KB to 4 KB this is free. And heap, we have 4 kilobyte until 6 kilobyte we have the heap, the dynamic memory allocation area, and we have the static, the stack. So as you can see, big chunk of free space is here. Again here, only program code, heap, and the stack is allocated. Free space takes up physical memory. Hard to run when an address space does not fit into physical memory. So what we can do when we map this address space into our physical memory, these free spaces will take up in our physical memory. So that is inefficiency of base and bound system of address translation. So what is segmentation? The idea is if as we have seen here, we have a lot of free space. When we transfer this address space into physical memory, this free space will take up in the physical memory. So the idea is why don't we have a base and bound register for each logical section in the process address space? This is good idea. So instead of taking all the address, the virtual memory into our physical memory, we can have the bound and base address for each code segment. As you can see, from 0 kilobyte to kilobyte we can have the bounds and the base address, and again for the heap and for the stack. So we will remove this unused memory, transferring into our physical memory. So segment is just a contiguous portion of the address space of a particular length, logically different segment. For example, we have code, stack, and heap. As we have seen here, we have code and we have heap and we have stack. So the other is no need because it is free. It will take up space in our physical memory. Each segment can be placed in different part of a physical memory. So the base and the bound exist per each segment. Okay, that is the idea. So placing segment in the physical memory, if this is our physical memory, as you can see, the base address is already set. For example, for our code, the base address is 32 kilobyte, which is given by the operating system. Then we have the size 2K, so the code will be here. The heap, as you can see, the heap starts from 34K because 32 plus 2 is 4, so it will start from 34K, and the size is 2K. The stack is the base address is 28, it's around here, and it has 2k, so this one is going up. Okay, consider this, don't forget. The stack is going in the negative direction and heap is going in the positive direction. We will see the impact of this, but the idea is placing the segment in the physical memory is assigned like this. So address translation on segment. Now address translation, the whole idea, we have seen it in our chapter 15, but the segmentation, how we gonna translate. So the physical address, this is a formula. The physical address is equal to offset plus base. Base is assigned by the operating system in the physical memory, and the offset will be found from our virtual the address space. So let's see, for example, let's assume the offset of virtual address is like 100. Here the code segment start at virtual address 0 in address space. If you see 100, most probably from 0 kilobyte until 100. So in the program code, somewhere around here we have an address, okay, the pointer, so 100. So how we find the physical address? So what we do, look here, the instruction is here at 100, okay, here in the top. This is, don't forget, this is just virtual memory, okay. So what we are going to do, 100 plus the base address for the code is 32 kilobyte. So 32 kilobyte plus 100, this will be 32,868 is the desired physical address of our virtual memory. In our space, in our virtual memory, it is 100, but in our physical, the exact code is found in the 32,868. This is the first case, okay, offset plus base. Now let's continue. Address translation on segment. Let's say, assume a reference to virtual address of 4200 in the heap section. Here, let's say 4200 in the heap section, we have to translate that. So what we are going to do, virtual address plus base address is not the correct physical address, because what we are going to do, let's say the heap segment start at a virtual address of 4096, because this is the address, the virtual address. So what we have to do, we have to get the offset. The offset will be, look, 4200 is here, this minus 4096, this will become 104. So this will be the offset in this scenario, okay. In this scenario, we have to subtract from the given address and the base address, okay, here in the virtual memory. Then once we get 104, then 104 plus 34k, because 34k is the base address in the physical memory for the heap. As you can see, the heap starts 34k. So we need this distance, this is the address 104, is the desired physical location. So in the first scenario it was 0 kilobyte, then we just have 100. In that situation we don't have any problem, because in the code section we can, but in this situation where it is in the heap, you have to find the offset. That is, you have to bear in your mind. Now segmentation fault or segmentation violation, fault or violation, if an illegal address such as 7 kilobyte which is beyond the end of the heap is referenced, the operating system occurs segmentation fault. Whenever, for example, the heap is until 6 kilobyte, but if any instruction comes beyond 6 kilobyte in the heap, then the operating system automatically notify this, and it is a legal address, and segmentation fault will happen. The hardware detects that address is out of bound. So in the address space, we have to take care of this. Now, referencing to segment. This is another idea in our textbook. We have the first approach is explicit approach. The explicit approach, what it does is chop up the virtual address space into segment based on the top few bytes of virtual address. For example, let's say we have 14 bits of address space like this, 0 until 13, and how we are going to check in which segment the instruction is. Example, the virtual address 4200 in the, as you can see here, 4200, we know it is in the heap, yeah? So what we do, we will change this into binary. The binary code of 4200 will be 0100000110101000. So this is the binary. So what it does is, the first 2 bits, it will tell us the segment information. For example, if the first 2 bits 01, as you can see, the segment is in the heap. If it is the first 2 bits 00, it is in the code. If it is 10, it is in the stack. So in this way, we can identify the segment. Okay, and the other is the offset information. This will be the offset information. And if it is 11, then this is other locations of the memory. Now, referencing to segmentation, this is a simple code. Okay, this is a simple code. We have segment mask. As you can see, we have the segment mask and segment shift. We have to shift the byte into 12. And offset mask, we have the hexadecimal representation. And if you see this code, get top 2 bits of 14 bytes. As you can see, this is what it does. Segment is equal to virtual address, segment mask greater than segment shift. Now get the offset. Offset is equal to virtual address and offset mask. Then we have if condition here. For example, if offset is greater than the bounds or the segment, then raise exception, because it cannot be. Or else physical address will be the base of the segment plus offset. We have the base, then the offset, then the register will be access memory from the physical address. So this is a simple code in our textbook. So disadvantage of explicit approach using 2 bits. The first one is if only 3 sections, then the 2 bits to store segment will wasteful. That means if we are using only 3 and this 1 bit, the first 2 bit will be wasteful. And the second one limits a segment size, maximum size, segment size of 4 kilobyte. And because of that, instead of explicit approach, we have another approach, which is implicit approach. The implicit approach, what it does is determines segment based on how the virtual address was generated. Example, if a program counter, then it is in the code area. So by learning how the segment, how the virtual address was generated, it will give us information whether it is in the heap, it is in the code section, or it's in the stack, or in other part of the memory. Now, referring to stack segment, let's see the stack segment now. A stack grows backward. Okay, it will grow backward. That means it will go up. the base will be starts from 20 kb, then when the stack comes it will go up. That means in the negative direction. Extra hardware support is needed in this situation. The hardware checks which way the segment grows, whether upward or downward. So in that situation, if it is 1, this is a positive direction. If it is 0, it is in the negative direction. As you can see, it is in the negative direction. So we have segment register, negative growth support. So as we have seen, we have segment here, code, heap, and we have the base, we have the size. Now we have additional information, the growth, positive or not. So if it is positive, it is in the positive direction, and heap and code are in the positive direction, but the stack is 0, means it is going upward, as you can see. So we have to minus. So let's see an example now, referencing to stack, how it does. So let's say this is our virtual memory, 16 kilobyte. We have the stack, we have the heap, and we have the program. So this is the location. Now, example, reference to a virtual address of 15 kilobytes. For example, let's say our code is in the virtual memory of 15 kilobyte here. So let's convert this 15 kb into binary 1111 0000000 0000. This is the binary representation of 15 kilobytes, and the hexadecimal representation will be 0x3c00. So what it does is, the first one is the segment. The segment will be 0 times 3, this one 0 times 3, and the offset will be 0 times c 00. So this will be 3 kilobyte and this one is 3. Negative offset means the offset we get is 3 kilobyte minus maximum segment size. In this scenario we have 4 kilobyte. So in this situation we have minus 1 kilobyte. So the physical address will be, this is equal to negative offset plus stack base. The stack base is 28 kilobyte. So 28 kilobyte minus the negative offset minus 1 kilobyte, it will give us 27 kilobyte. So if you see in our table here, we have the segment information, we have the base information, we have the size information. Now additional, we have the growth, whether it is negative or positive information will be included here. So this is a simple example. You have to take care whether in the virtual memory, whether the stack or the heap is positive or negative. We have to see that. So the segment register with negative growth support. This is the example. For example, support for sharing. Support for sharing is a simple idea. What it does is, for example, we have a shared memory, a code section. So we have process A here, we have process B here. So both processes will use this code, okay? And they assume that they are using their own code. But what is this area is the shared memory area. So in this situation, we gonna add additional row column for the protection. As you can see, read execute, read write. So we have to give additional byte to protect this code section, so the other processes can use the code, but they cannot make change on the code. So the segment can be shared between address space. Code sharing is still in use in systems today by extra hardware support. Extra hardware support is need for form of protection byte, a few more bytes per segment to indicate permission of read, write, and execute will be added. So this is the idea of shared memory. Fine-grained and coarse-grained is another idea. The coarse-grained means segmentation in the small number. For example, in our situation, we have core segment, heap segment, and stack segment. This is a coarse-grained type of segmentation. But if it is fine-grained segmentation, allows more flexibility for address space in some early systems. To support main segment, hardware support with segment table is required. So operating system support for the fragmentation and managing fragmentation. For example, external fragmentation means little holes of free space in the physical memory that make difficult to allocate new segment. For example, let us say there is 24 kilobyte free, but not in one contiguous segment. The operating system cannot satisfy the 20 kilobyte request. Let's see. For example, as you can see here, this is free, this is free, this is free, from 16 kilobyte to 24 kilobyte, from 32 to 40, from 48 to 56, but they are not in the same location. So even if the total is 24 kilobytes, but if we need 20 kilobyte of memory space, we cannot, because it is fragmented already, as you can see here. So the operating system cannot satisfy the 20 kilobyte request. So what is the solution? The first solution is compaction. Compaction means rearranging the existing segment in the physical memory. So as you can see here, we have free space here, we have free space here, we have free space here. So what we have to do, we have to compact this like this. Operating system will take until 16 kilobytes, from 0 to 16. Then the allocated code will be here. Then from 40 kilobyte to 64 kilobyte in the physical memory, we're gonna use it like this. So the idea of compaction is to rearrange the free spaces in one memory. Then the operating system can easily assign any request of memory. So to do that, and the first thing is compaction is very costly. What it does is, first, you have to stop running processes. Second, copy data to somewhere else. Then change segment register values, because all the process which has bounded base register, it should be changed accordingly. So it is very costly to do that, because as you can see, when we reallocate from, for example, 24 to 32, from 32 to 40. So when we reallocate, we have to change the register values as well. So we have another better idea, better algorithm. Better to use a free list management algorithm. Keep large extents of memory available for allocation. And the approach will be the best fit, worst fit, and value algorithms. These are the idea. So compaction and this free list management algorithms. So this is non-compacted. In the non-compacted situation, this is our physical memory. But after compaction, as you can see, our physical memory looks like this. So in a nutshell, that was chapter 3 of the book. And we have seen memory compactions, managing fragments like free list management algorithms, what is fine-grained, coarse-grained, and support for sharing, what is memory sharing, and we have seen also reference to the stack, and reference to the stack again, and segment, referencing to the segment, how we use the top 2 bits, the top few bits. It will tell us if it is code, it is 00, if it is 01 and 10, and again segmentation for the legal addresses. And this is the heap, referencing how address translation on the heap. We have seen, take care, we have to use the base address, and we have to get the offset, then we have to add it into the base. And again, address translation on segment. As you can see, if it is 0, then again we have to get the offset, and we will add that offset into our base address, then we will get the physical direction. And this is placing segment in the physical memory, how it is assigned, and what is segmentation. The idea of segmentation is to alleviate the problem of base and bound. And as you can see, we have a lot of free space. If we use base and bound in the whole in the whole address space, the virtual memory, we will transfer all this free unused memory to our physical memory. That will be a problem, so that's why we need segmentation. So in the nutshell, that was the chapter 16. I hope it was helpful. And this is Engineer Selassie from Maybe Academy and Brain Boosters, and the next time I will come up with the new chapter 17. Until then, bye bye. Thank you.